Very good afternoon, folks, and welcome to the second of the SpotLYTT webinar series. I'm Pradyumna Thiruvenkatanathan, and I'm one of the co-founders and directors of LYTT. Today, we'll be talking about LYTT's downhole sand monitoring product and how the technology is fundamentally redefining sand management practices within the oil and gas industry. I'm joined today by Alberto, one of our super talented petroleum engineers. Alberto, please can you say a few words to introduce yourself?
Yeah, sure. My name is Alberto Mendoza, and I have a petroleum engineering background. My experience is with my previous experience is with two of the largest oil and gas operators, working several producing assets around the world. At the same time, I've been keen in learning more or exploring the benefits of data science in transforming or making more efficient our current industry practices. So before LYTT, I spent some time leading the research project for oil and gas applications at the data-centric engineering program at the Alan Turing Institute. And here I am with LYTT.
Fantastic. Okay, let's get started. Let's start with the business challenge. Sand management remains one of the key production challenges in the oil and gas industry today. This is because many of today's highly productive reservoirs comprise of what we refer to as weakly consolidated rock. What this means is that as we produce oil and gas from these types of reservoirs, they quickly disaggregate and produce sand along with the hydrocarbons. For those who are not from the oil industry, a good way of thinking about this is if you imagine the reservoir to be a sponge. If you take a sponge and dip it in water, it would take in some of the water as it has the porosity. But when you take it out of the water and gently squeeze it, it lets the water flow out, which is what we call permeability. When we release the pressure, it also goes back to its original shape as it has the elasticity to do that. Young hydrocarbon reservoirs that hold oil and gas, however, may have good porosity and permeability, but may not have the elasticity or the strength to keep to shape once the pressure is applied. And this results sometimes in cracking of the rock. And in consequence, this releases sand. Sand, as you may know, can be quite erosive, and at high production rates, sand tends to erode the piping in the wells, causing well integrity risks. You may have seen sandblasting in action, as you can see in this nice little image, to remove paints, but imagine doing this constantly from inside the pipe at much higher rates for hours, days, weeks, or even months. This obviously raises significant risks from a well integrity perspective. If it is established that the well is consistently sanding, they are choked back to minimize sand production and erosion risks. This, however, implies that the well's production performance also gets a hit. This may mean an offshore well that has been set up to produce higher rates of oil eventually may end up producing just a small fraction of what it was supposed to, consequently resulting in pretty significant production losses. Production deferrals can sometimes be as high as 90% of the well's production capacity, making this one of the industry's key technical challenges to solve today. Let's talk about today's approach. The typical approach in the industry to circumvent the challenge is to first install sand control completions like gravel packs that act as filters to prevent sand from being produced. These are, however, quite hard to install several kilometers underground, and changes through the life of well also leads to challenges in maintaining its integrity, eventually leading to sand production. Most operators today tend to take surface measurements like sand samples or use acoustic sand detectors to identify sand presence. This, however, gives little to no indication of where the sand is actually coming from, which is a key question to answer if you wish to fix the problem. This, therefore, requires surveillance downhole and not just on the surface. A good analogy here is if you have a cut in your hand and want to put a plaster on it, unless you know where the cut is, there's no use for a plaster. This is where LYTT's new downhole sand monitoring system comes in. And what we offer is a unique field-proven technology that lets you identify, one, where the sand is coming from in the well, which reservoir section, two, when the sand gets produced, three, and relative estimates of sand production, all just with a single fiber deployed across the well. What's more, the technology does not require any added electronics downhole, can be completely non-intrusive, does not require any downhole power or communications, and it also gives you a real-time indication of sand production 24/7. Sounds too good to be true, doesn't it? But that's really what it does. And here's a nice video that describes the technology.
To produce oil and gas, you need to know your hard rock from your soft rock. just like your music streaming app uses complex algorithms to distinguish between rock, jazz, and classical, we use this 2 miles beneath the sea floor to listen to different sounds made by liquids, gas, and solids. We put miles of fibre optic cable inside a well. We light up the cable, and it acts like a distributed array of microphones, recording sounds deep underground by modifying the light. Just like your music app, we use complex algorithms to pick out specific sounds or acoustic signatures and match them to our database of known events, like adding them to a playlist. We're listening for specific sounds, like sand entering a well or building up, or gas bubbles in oil. Also, we can work out exactly where the event is happening. So once we know which event is happening and where, we can work out what action to take, like adjusting the pressure or cleaning out the well. Innovation found, sounds underground.
All right, so hope you enjoyed the video there. Let's talk about some of the challenges in executing this capability. One of the key concerns that we had to address when we first started working on this technology was around big data. This is because each DAS system produces about 10,000 samples of data a second across every meter in what is usually a 10-kilometer fiber. And to put that in perspective, that's about 100 million data points a second coming in from the DAS unit, and that translates to about 1 terabyte of data every hour. That's equivalent to 1,000 movies worth of data every single hour. So you can see the volume of data here. And instead of compression, what LYTT offers is an intelligent data extraction and processing capability that extracts the features in the signal that are most relevant to sand entry point identification and discards the rest of the data, reducing data volumes by over 2,000 times at site. The processed feature data is then transformed into sand logs in real time through a cloud-based software and presented to the end user for operational decisions within seconds, almost like the Shazam, but for the oil wells instead. Alberto, do you want to show some case studies so the folks can see how the technology has been used in the field before?
Yes, of course. Let me first start by introducing the concept of a sand log. So Prad has mentioned a couple of times the idea of sand log, and you've seen from the video, basically we extract or we receive acoustic signals from the fiber deployed downhole. And from this acoustic signal, we extract the characteristic attributes of sand entering the borehole. And so we use signal processing and pattern recognition procedures to do this. And essentially, we remove the fingerprint of sand from background and of low noise. So then that characteristic signal to sand entering the wellbore is what we call a sand log. Okay? So now let's look at an example. This is from a well where the sand log was key information to design a remediation job. So what you're looking at now on the screen is a sand log. So let me just describe the chart. So vertical axis is the acoustic, normalized acoustic amplitude, so our signal. And then in the horizontal axis, you have measure depth. So for now, let's focus on the curve shaded in red. That is a sand log prior to remediating the well. So what you can see in the intervals where the amplitude is high, and that means that those particular intervals are producing sand. And as you can see, it gives the opportunity to design a very precise targeted remediation job, because you can identify the precise intervals that have sanding problems. And for this particular well, those are shaded in pink. And so based on this, the remediation job was designed. And here's an example of when the expandable patches were placed in these intervals of interest. So basically, you run a self-expandable patch to isolate those zones that are producing sand. So to basically block production from those and stop sand coming into the wellbore. So once those patches are set, and they block these problematic intervals. Then you can ramp up your well again. And here is, again, we go back to our previous figure, but now let's focus on the blue sand log. So that is the sand log post-remediation. And what you can see compared to the pre-remediation sand log, or the red one, is that now the sand production has significantly reduced, and it has in fact been completely eliminated in some of the previously sanding intervals. So as a consequence, the well can be further binned up, or its rate can be increased more than it was before, because now you don't have a sanding problem. So what you're seeing in the screen here is the oil rate before remediation. And the dots in yellow, those are sand, it's sand detected at surface. So you have a sanding problem here. The well is choked back because of the sand problem. Then it's shut in, remediated. And then the well is open again to a higher rate. Sand is significantly reduced, and oil production is increased. So the result in this well was a 90% reduction in sand and about 2.5 MBOD increased in production. So that's about $60 million per year. So basically 3 barrels. Now let's look at another example. This is a well that it was completed with an open hole gravel pack. So one of those types of sand control equipment. And it as well has, this particular well has a permanent fiber installation. So what you see in the screen in the middle is it's a gravel pack log. So basically it shows you the integrity of the completion. And what it shows is that it's an ineffective gravel pack, so it's incomplete. So you see some blue intervals, and that means that those intervals, the gravel was incomplete. So it would permit sand to come into the wellbore. So because this well had a fiber installed, then we wanted to look at the sand log and compare it to the gravel pack. And what's very obvious here is that we see very good correlation in what the sand log shows as sand entries to what the gravel pack log shows as an ineffective or incomplete gravel pack. Now, so this is quite informative, but now imagine having this sand log every second, or having this in time. So this would allow you to monitor not only further deterioration of your completion, but also any changes in the sanding profile as a result of any changes in the operations of your well, i.e. rate, drawdown, etc. So this idea opens the window for the power of real time. So now if you could monitor in real time a well with the sand log, there's a number of things you can do. And so to put that in a better, more descriptive way, here's an example of a well where now, let me describe first the figure. So if we look at any of these, or the one on the left, so the vertical axis is depth and the horizontal axis is time. So now we have one of these sand logs I showed previously, but in every second. So you put this now as an image, and you can see basically in time how the sanding profile of the well is changing. But first, if we look at the one in the bottom on the left, what it shows, so the colors, the red and blue, that's the signature of sand, or our sand log, as I said. So the red is sand entry. So what we can see here is through the interval of the open hole gravel pack, or the reservoir interval, we have a interval. We have a very persistent sand entry point. And then what we see as the sand is lifted and it's traveling through the tubing in the upper completion to the surface. So we open this depth interval to further up all the way to surface. Then you can clearly see sand lifted or traveling through the upper completion tubing all the way to surface in the form of slugs. So it's being lifted in periodic way. Then this well was shot in because of the sanding problem. And what you see is when the well is shot in, you see the sand falling back into the well bore because it has no more energy to be picked up to surface. So this sand will be falling back to accumulate somewhere in the well. So that's the power of real-time DAS sand log monitoring. You can see that you can basically map sands from its source all the way to surface and back. Now, just to stress the point of what I just described, here's another example where, again, we have depth in the vertical axis and time in the horizontal axis. And I want to point to your attention the red curve at the bottom of the figure. That one is the sand detected at surface by an acoustic sand detector, so it's in the flow line. And what you see is some spikes here, so those are significant sand seen at surface. So then we go to our sand log or our DAS monitoring. What we see is, first is a yellow continuous line. That is sand accumulating somewhere in the upper completion. And then as the well is ramped up or its rate is increased, it's lifting sand in slugs. And these are these lines that you see curving up, which correlate really well with sand seen at surface. And then at an optimum rate, what you see is that the accumulation has disappeared. So now the rate of the well has been increased enough that the well is cleaning up. Basically, it's no longer accumulating sand downhole. And at the same time, in this case, it's not producing sand from the reservoir. So this sort of optimum operational envelopes is something you can design based on the insights of this real-time DAS capability. And therefore, you don't defer production as a consequence of sand problem. But in addition to that, you prevent your well from being restricted due to sand accumulating somewhere in the completion. And so this has given very good results, and it has added significant value in protected production or increased production in several wells, particularly in a large field in the Caspian. So Prad, maybe you can tell us a bit more about the record of deployments of the technology.
Sure. The technology has now been deployed over 170 times, adding thousands of barrels of oil per day as a direct consequence. The value has come from 3 different buckets, one around base protection, the second around drawdown optimization, and third around sand remediation. Okay, so now that you've heard about the technology, seen it in action, and also seen the value it can bring to our customers, I think it's a good time to turn it around and open it up for questions. So let's go on to the chat window and see what questions we're getting. All right. We've got one question coming through. All right, the first one is, can we use fiber optics for other surveillance needs like inflow profiling? Alberto, maybe you can take this one.
Yeah, sure. So yeah, good question. Thanks for that. So we've shown you and more or less conceptually in the video how we extract, or we can extract, the characteristic signal of sand from this acoustic signal coming from the fiber. So in a very similar way, we can extract the characteristic signal for, let's say, oil or water or gas. And that opens an opportunity for another application, which is inflow profiling, where you can monitor production of what you actually want, or in terms of fluid, not necessarily sand.
Okay. The next one, I see a few more coming in. There's one from Dennis, which says, were the 170 applications for one operator, and did they represent 170 wells? Okay, so that's 170 deployments is what I'm talking about here, Dennis. So it's application of the technology across, I believe, around 50-ish wells. But you have repeat jobs as well that are done in order to optimize and base protect. So it's 170 different runs, and this has been used, as I said, for base protection, drawdown optimization, and remediation as well. There's one from Henry Garcia, which says, what are the main challenges processing the signal from DAS to get useful information? Good question, Henry. So in terms of the DAS data itself, I think we did mention this during the talk, it's the volumes of data you're getting. Each DAS system produces 1 terabyte an hour roughly of information. So that's huge volumes of data. And people have considered compressing it and then trying to transfer it and then analyze the data post the fact. But you can understand if you want to go into a real-time permanent surveillance type capability, this is not really an answer for that solution, for that challenge. So the key issue here is to try and understand what to extract from the acoustics in order to make meaningful signals or construct insights from it. And this is where LYTT's been working quite hard. And what we've done there is built not just the algorithms or the features that are relevant, but we also have a backend data infrastructure that's been set up, a cloud-based infrastructure that lets you extract what's useful and then transform that into insights in real time. And we have a data management platform as well to support real-time decision making. Okay, there's one from so there's one from Christoph, which says, what's the typical fiber optic cable deployment method behind tubing? So maybe I can take this one, Alberto.
Yeah, go ahead.
So we have looked at different deployment methods. So the ones we are talking about here are pretty much behind tubing, but permanently installed. We've also run interventions in the past just to see differences. And what I can say is that we can detect sand, whether it's an intervention fiber, whether it's inside the tubing or even outside the tubing. Okay, and then there is one from Damiet Thomas. My name is Damiet in Nigeria. I saw your LinkedIn profile. Happy to join the webinar. There are lots of sand production challenges in the Delta region of Nigeria. Do you consider working together to deploy this to operators in Nigeria? The answer is yes, Damiet. So please feel free to reach out to me on prad@lytt.com and we can take the conversations further. Okay, there is one. How do you know what the signature of sand noise is? Maybe Alberto, you can take this one.
Yes, sure. So the way we do this is we have basically a laboratory or a control environment, which consists of a flow loop where we have permanent fiber and we can inject fluids and sand at high rates or variable rates. And so we acquire data on this controlled environment and we analyze this data. And this is how we identify the particular characteristics or signatures or fingerprints of sand, which we use to build our algorithms, and then we test them on the field. That's basically how we do it.
Okay. There's one again from Damiet. Since your solution is a permanent installation, do you require maintenance? And if yes, what are the maintenance requirements? So I think this would depend very much on the type of installation we have. So there are different ways in which you can install permanent fibers. There are some in which you would have control lines and then you would install the fiber within control lines. You have other methods where you have fiber optic cables sort of strapped to the tubing as well. So in terms of the lifetime, it would very much depend on the type of installation, but I wouldn't be surprised if you can run these for years without having any issues. And in terms of the data management platform itself, it's a cloud-based infrastructure that LYTT provides. So in terms of processing and data management support, we can offer that, and it's quite scalable as an infrastructure. Okay, and there is one more. Maybe this is for you, Alberto. Can this only be done in wells with fiber installed?
Good question. Not necessarily. So ideally, if you have the fiber permanently installed, then you can monitor permanently. But all you need is a fiber downhole in the well. So we can do this, and we've done it as an intervention where you deploy the fiber optic with a wireline downhole. You just let it sit there for hours or days. You lock during this time, and then you retrieve the wire. So the answer is yes. You can do it both with permanent installations and interventions.
Very good. Okay, there's one from Hiru. Any example application on subsea wells? Good question, Hiru. So far we've been looking at offshore dry tree completions, but obviously in terms of the applications, it's not limited to offshore dry tree. We can go subsea as long as the fiber is in there. So we don't have one to demonstrate specifically in a subsea well right now, but having said that, I think the capability equally scales, so it doesn't matter if it's subsea or not. It's just the fiber installation and the configuration that's going to that would require a bit of consideration. Okay. All right, there's one from Sina. Hi, I just joined. Sorry if my question has been answered before. Do you localize the sand entry points or just say if the well produces sand in general? So to answer your question, Sina, maybe Alberto, you can take this.
Yeah, sure. So the answer is yes, we can. And that was one of the first examples that we showed today, where you can identify the sand entry point with some good precision. So indeed, you can use the DAS sand log to specifically identify the interval of sanding within meters. And the example that we showed is that this is very key it's key information in designing targeted remediation jobs, for example.
Okay. All right. There is one question around. In fact, there are a couple of questions which talk to the same thing. What is the minimum sand rate that you can be detected? And there's one from Stuart as well, which says, can you infer rates from your results? Okay. Should I take this one, Alberto?
Yeah, go ahead.
Okay. In terms of sand rates, there is a distinction that is to be made when you talk about rates and when you talk about the sand that is being produced on the surface. The surface volumes are different to what comes downhole. And the reason I say this is because you may have sand production in a localized setting downhole, but once it comes into the well, it dilutes with all the other zones that are now producing oil but not sand. So when you measure, let's say 1 pptb on the surface, that could also mean you're producing 50 pptb from one parts per thousand barrels from one section in your well, which then dilutes. So on that basis, we have done some studies and we can detect there are different wings to the answer here. So we can detect down to a few pptb of sand at the influx points, but that would also depend on the mass volumes that you're talking about. So what is the particle size distribution of the sand, right? So it would again come back to, if you're using this for sand detection, you would also look at the gravel pack and what it would let through. So we are able to detect anything above 50 micron sand and a few pptb at the point of influx. Okay, there's one from Jim. How portable is the sand signature from one well environment to the other? So good question, Jim, and this is something we've been working quite hard on. You will see that the signature is similar, but you will require calibrations in the data. So a nice analogy here is if you are sneezing, Jim, and Alberto here sneezes, both of you are sneezing, and without looking at both of you, I know you're sneezing, but then the noise, the sound that you make, the voice that you have is different. So I would then have to best ascertain whether you're sneezing or not, I'd have to get some idea of your voice. So you'd need to do a bit of calibration. And what we have is a technology that embeds the calibration as part of the offer. So you get automatic calibrations built in, and from well to well, it just automatically calibrates itself and then identifies sand. Okay, let's look at any others. And in the interest of time, maybe we should just finish with one more. Okay, there's one from Damiet again, which is, since data processing is cloud-based, how many wells can your DAS be limited with respect to data acquisition and processing, and how fast? Okay, this is more a combination of hardware and software, right, Demian? So you would have, if one fiber is connected to the DAS unit at one instant in time, so you would have instance in time, you would be measuring on that one fiber. But you can equally switch between multiple wells in the DAS. But in terms of your software offer here, this is a cloud-based infrastructure. So the data can be passed straight into the cloud and all of the processing happens. And because it's cloud-based, we've also designed it to be highly scalable. So if you have more wells connected on, we could quite easily take the data and we can scale it. All right. So with that, I think we should close it. It's just past time here, so we're just going to show ourselves and wave our hands, saying thank you very much. And we're going to sign off now. So thanks again for all your questions. It's been great talking to you guys, and look forward to the next one.
Yeah. Thank you for joining, and thank you for the questions.
See you guys later.